This is the Building Automation Monthly Podcast with Phil Zito, episode 113. Hey folks, Phil Zito here, and welcome to episode 113 of the Building Automation Monthly Podcast. In this episode, we are continuing How to Program. This is part 2 of the How to Program series. And in this episode, we are going to be covering common logic blocks, how to interpret sequences to code, code layout and design strategies, and then the secret to fast coding. Alrighty, anything that I mention in this episode will be available at buildingautomationmonthly.com/113. Speaking of things to mention, if you haven't seen it yet on YouTube, I have restarted the BAM TV series, and I have gone and released episode 1. All future BAM TV series videos are going to correspond with the podcast episodes. So if you're someone who likes to learn visually, then you're really going to want to check out the videos. They won't be the exact same as the podcast episodes. Don't worry, I'm not going to subject you to listening to me twice, but they will be similar. They will provide a visual aspect of what we cover in the podcast episodes. So with that being said, let's dive in. So logic blocks, I talked through logic blocks in the previous episode. I kind of hinted at them, talked through them, talked around them, talked over them, but I didn't talk about them. So what are logic blocks? Well, as I mentioned, back in the olden days, and some manufacturers still live in the olden days, but most have moved on, using the concept of abstraction. So abstraction is where you take things like line code and you add a visualization layer to them so you can do block programming. Block programming is where you take functional line code and you transform it into visual blocks that you can drag and drop. It makes programming so much easier. And within the realm of logic block programming, there are 6 main types of logic blocks. Now, granted, in my programming course, I go through many more types of logic blocks. We spend about 3 hours on logic blocks, but in here, we'll spend about 10 minutes. So, with that being said, the 6 main types of logic blocks you want to focus in on are Boolean, which, as we remember from the previous episode, Boolean means true, false, on, off, 1, 0, 2 states. And then we have comparative. So we have comparative logic. We have math blocks, flow logic, sequence logic, and loop logic. All right. So something you really want to focus in on are these 4 types of blocks: Boolean, comparative, flow, and loop. If you learn anything, and I mean anything about programming, if you learn those 4 types of logic blocks, you are going to be sitting pretty. I'm serious. You can write pretty much every program you need with those 4 classes of logic blocks. Pretty much every programming. There are some where you'll need math blocks, sequence blocks, timers, etc. But for the most part, those are what I call core logic blocks. So what are they? Boolean. Boolean, as I mentioned, is a true-false on-off value. So think about it this way, right? You have 2 main types of Booleans. You have and you have or. Now, the name of the block should already tell you kind of how it works. An and block has 2 or more inputs and 1 output. And then based on these inputs all being true, because remember the Boolean blocks, there are only 2 states. If all of those inputs are true, then the output is, you guessed it, true. Now OR blocks, on the other hand, they look at a OR scenario. So AND blocks are usually written for conditional starts, where you want all of the conditions to be true before something happens. A common example of this would be to make sure the economizer damper's open, to make sure you're not in low alarm, to make sure you're not in low pressure alarm or high pressure alarm. You want to make sure all of those are true before you go and start your fan or start your pump or whatever. Okay? Now, OR blocks on the flip side are where you're looking at an OR scenario. So if any of the inputs are true, then the output is true. These kind of scenarios are usually used for states or failure scenarios. So if you want to go and generate an alarm that will switch your lead lag, you would use an OR block where you could say, if any of these alarms are true, I'm going to switch from lead to lag. Or if any of these states are true, or conditions are true, I'm going to enable this state. So you really want to think through. And quite honestly, depending on how you code, you could use and or blocks to accomplish basically the same thing. It's just in how you do it. Now, comparative blocks. My personal favorite blocks, these blocks in my opinion are underutilized. And why do I say that? Well, a lot of folks who are new to programming write the omnibus program. Now, what do I mean by that? I mean that every mode is enabled at the same time. You have cooling, heating, preheating, economizer, fan, ventilation, dehumidification, humidification. Everything's enabled. Because why not? And that makes a very inefficient program. It's the reason why so many folks struggle with PID loops. They don't struggle with PID loops because they can't properly set the settings. They struggle with PID loops because all their freaking PID loops are running all the time. And because they're running all the time, they're never properly tuned and they're all just out of whack and they're spun up, they're wind down because folks don't use comparative logic. So if you take a comparative logic block like a greater than, and you say if zone set point is great or zone temp is greater than zone set point, then I am in cooling mode. Then my cooling PID loop can be enabled. Otherwise, my cooling PID loop is not enabled. You should never have your PID, don't want to say never. I promised myself I wouldn't say never. Very rarely should you have your PID loops enabled when you're not in that state or in that condition. Just trust me on that. Next up are math blocks. Math blocks are basic. They're basic upon basic. There's really only kind of two catch-alls you have to pay attention to. The first is math blocks are addition, subtraction, multiplication, division, averaging, summing, low select, high select, etc., right? So, what do you have to be careful with? Well, first is the division and the subtraction. 2 divided by 4 is a completely different result than 4 divided by 2. However, 2 times 4 is the exact same result as 4 times 2. So, when you are doing math, you need to pay attention to subtraction and division blocks. Addition and multiplication, you can pretty much do whatever the heck you want. Then, on summation and averaging and low and high selects, you got to be careful about how you manage your averaging and your summing. You need to make sure that if you're doing sums or averages, that they all totalize up, that all the values totalize up before you do the sum or the average, and that you got the proper count. I've seen too many programs where they missed the count, it was off by 1, or they missed an object in totalization, and because of that, the average was off and the program never controlled right. Flow logic is beautiful. Flow logic is like, I don't know how to describe it. It's just a beautiful set of logic blocks that allow you to do wonderful things like looking at if you're in occupied mode or unoccupied mode and then switching your set points so that you don't have to have unoccupied and occupied set points. You just have 2 values in the switch and you switch between based on occupied and unoccupied, because I'm a firm believer that you should have 1 set point for your end user because you're making their life very confusing if you give them 4 set points. Think from the perspective of it's the janitor running the VAV box. Not saying all operators are janitors, but I am saying some janitors are operators, and that can be very scary. So you need to prepare for that. In addition to flow blocks, you have things like muxes and demuxes. Think about an occupancy point, right? An occupancy point gives you occupied, unoccupied, standby, off, and a variety of other potential modes. Well, that is 4 different states right there that I just described. Those 4 states go into a multiplexer block, also known as a mux block. And then that block, based on which state is selected, it passes through a logic stream. That is extremely powerful if you want to build state-based logic, which is how I recommend you program your code. Then we have sequencers. Sequencers, I don't know why, but actually I do know why. Folks seem to struggle with sequencers. They just seem to have a hard time with them. And I get it. Sequencers can be very intimidating and confusing. In my opinion, for a new programmer, they can be more confusing than a PID block. Because, think about it. With a sequencer, what is its purpose? It's to take an analog input, typically 0 to 100%, and then drive a series of Boolean outputs on or off. It's also known as staged control, sequenced control. Use it for staged reheat, use it for staging chillers up and down, use it for staging your DX coils, etc. It has a lot of variables in it, min and max runtime. It has your loading and your unloading parameters. So basically, it could say, hey, stage 1 comes on when you've been above 24% for 5 minutes, and then it runs for 5 minutes, and when it goes below 20%, it goes off, and it stays off for 5 minutes. And that can confuse a lot of people. They're like, hey, I'm at 70%, but none of my stages are turning on. Well, that's because stage 1 is off. And stage 1's min off time is off. And the way you have your sequencer set is that it needs to turn on stage 1 first. So you could go and make your sequencer where even if stage 1 is off, it turns on 2 and 3 and 4. That may work. That may be a bad scenario, depending on how you're supposed to control the systems. So with that being said, sequencers can be very, very confusing. And then we have loop logic. And I'm going to link to a 30-minute video that I did on PID loops. I'm not going to try to explain PID loops on this podcast episode. That would be painful for me. It'd be painful for you. Probably be painful for whoever's sitting in the car with you. So we're not going to go through that. What we will do, however, is we will talk about what PID loops are. So basically, if you recall from the previous episode, a controller is a computer basically in a box. It's got a processor and it runs logic in a loop. It starts at the beginning of the logic, works its way through all the logic, and then restarts. Well, that is what loop logic is. PID loops look at the error, the difference between set point and process variable. And then it looks at your proportional and your integral values and sometimes your derivative values if you're using derivative, which you should not be using. All right, listen to the whispering voice. It knows all. In all seriousness, though, most of the time, PI loops will be just fine and derivative will just give you a headache. With that being said, however, your program loops through the code. And after looping through the code, it goes and determines what the output of the PID loop should be. So it compares the error and how long that error has existed, does a math calculation, gives you an output. So when you're tuning your PID loops, that is what you're tuning. So how do we take code, or rather sequences, and turn them into code? That literally is the $100,000 a year question. Why do I say the $100,000 a year question? Because I'm a firm believer that if you know how to program effectively, I'm talking not little baby programs where you're writing VAV box programs and saying, I'm a programmer. And you're like, no, you're someone who can program VAV boxes, which, yeah, that's not programming. No, I'm talking about where you're doing complex central plants. I'm talking about where you're doing complex air handlers. If you can write that kind of code, you can print your ticket, at least here in the United States, to $100,000 a year in salary. I'm serious. Man, I'm probably going to piss off some of you owners who are listening to this podcast. And you're like, don't tell my techs this. But in reality, if you are a friggin' good programmer, you should be making $100,000 a year. You should, because that is a skill that is at least 4x what you are being paid on your hourly rate. So I'm going to just do a brief segue real quick because I realize some of you who are techs may not understand how your salary is calculated. You may not give a crap, but I really recommend that you do give 2 cents about it, because this will determine how you get your raises, how you get your promotions, and it'll give you leverage for negotiating for yourself. Okay, so here's how this all works, right? So you're paid an hourly rate, even if your salary. And what I mean by that is $100,000. That's $52 an hour. Now, factor in insurance, factor in a bunch of other stuff, and you're at about $70 to $80 an hour. I need, as a business owner, to make 2 to 4x times your hourly rate in order to turn a profit. And profit is all that matters. Revenue doesn't matter, because you can revenue and be negative on profit. Profit is what keeps you in business. So when you're an installer, whether you like this or not, you're doing work that is barely break-even work. That's why I'm such a firm advocate of subbing out install to electrical subcontractors. Have them absorb all the risk, get a guaranteed price, and then go and take the high profit work that you can focus in on, like programming, like designing, like doing stuff that is customer facing, where customers are seeing value. That's the stuff you can bill $140 to $180 an hour for. That's the stuff that will go and be 2 to 3x your hourly rate. That's stuff that allows you to pull in anywhere from 15 to 35% margin, which is really, really good, because that makes you money. Margin means your company stays in business. Okay, so when you learn programming, you're learning a highly valuable and profitable skill set. Does that make sense? No one may have ever explained it to you this way, but you have to understand, I used to run a $60 million ops group. I had 22 techs under me, and when I took over the ops group, we had $2 million. That's $2 million that were accounts receivable past 720. What does that mean? That means folks owed us $2 million from 2 years ago. You can imagine that is bad. That's very, very, very bad. I was able to turn that around by getting the technicians to think about profitability, helping them understand how many hours do they have in the job, what's the profit margin of the job, what tasks can they put more hours into, and what tasks should they try to avoid putting hours into. By having that mentality, you're able to be profitable. Your projects are profitable, which then gives margin that can be applied to your salary. That's how you get raises. That's how you get $100,000 a year. All right, off my soapbox. Back to sequences and coding. All right, so sequences and coding. So basically what you need to do is you need to go and interpret sequences into code. This is going to determine whether your sequences are awesome or whether they're giant, smoking, steaming hot piles of turds. That's the reality. And what do I mean by this? Well, when you get a sequence, you're oftentimes not going to be handed something that says, these are all the inputs, these are all the outputs, these are all the process variables, these are all your Boolean modes, analog modes, these are all your safeties. So you need to determine that on your own. How do you do that? I like the highlighter method. You get 5 highlighters. And this is where, if you have to pause this to write it down, to grab a notepad, this is really important. So jot this down. 5 highlighters: yellow, pink, blue, orange, green. You can pick all those up at a local Walmart. Yellow is for your inputs and outputs. Pink is for set points and variables. Blue is for Boolean modes, orange is for analog modes, and green is for your safeties. So that should sound familiar to the 5-step programming process that we went through in the previous episode, which if you haven't listened to that, go back and listen to that episode. It's the one right before this one, episode 112. All right. So with that being said, now you go through the sequence, you print it out, and you highlight all your inputs and outputs in yellow. You highlight your set points and variables in pink. You highlight all your Boolean modes in blue, your analog modes in orange, and your safeties in green. You have now highlighted everything you're supposed to program. Now you need to go and order and number these. So for example, in the YouTube video, I go through a rooftop sequence of operations and I challenge the viewer and I say, hey, what, when you turn on the rooftop, is the first thing you should have happen? And a lot of folks will say, turn on the fan. And that's absolutely wrong. It's open the dampers. 9 times out of 10, you need to make sure you open the dampers before you ever turn on any fan when dealing with air handling systems. So with that being said, you're going to find the damper logic and you're going to put a 1 next to it. That's going to be the first thing that needs to happen. Then you're going to find your supply fan logic. That's going to be the second thing. And you're going to reorganize this, and that is how you're going to program. Now here's where it's going to get a little confusing, okay? Because you can do one of 2 ways. If you're the one writing the sequence, then you can rewrite the sequence so that it flows in this way. Most of the time, you won't be the one writing the sequence. You'll be at the mercy of the controls engineer or consulting engineer, whoever's writing the sequence, right? So what you'll do is you'll take this numbered so you'll know what to program, but then you're going to look at the sequence and you're going to write the code in the order it appears in the sequence. Now I know that goes against everything I've told you so far, because I've always said don't code according to the sequence because you'll miss things. So here's the caveat with that, right? There's always a caveat. But when you look at that sequence, when you look at that rooftop sequence, and I'll link to it so you can see it in the show notes. When you look at the rooftop sequence, there's actually your zone variables first, then your fan, then your low temp safety, etc., etc., etc. Just because you are following the sequence and writing code in order does not mean you write all that in the order you read it. I know that's confusing, but here's what I mean by that. So you start with your inputs and outputs, left and right. Then you start with your variables. Then you start with your Boolean modes. Your first Boolean mode that you'll come to is temperature, is your unoccupied and occupied states. The second Boolean mode you'll come to is your fan command. The third Boolean mode you'll come to is your damper. So you're going to write those codes. Now the thing is that your temperature is going to go at the top. Your fan will come right after that. And your economizer is actually going to go at the bottom of the program. Now I know this is a little hard to visualize in the podcast, but the reason you're doing that is because in the sequence, the temperature control or temperature settings for choosing whether you're in cooling or heating mode is at the top of the sequence. The fan is right below that. After that is low temp safeties, but we do safeties last, so we're not going to have that on our sheet yet. And the economizer is the last thing in this sequence, so we move it to the bottom of our code. So even though we are writing in the order that we determined, we are still following the sequence. So we will write the different segments of the sequence in the order we laid out based on our 5-step process. But where we put what we write is determined by where it is in the sequence. Does that make sense? I feel like I talked around that a couple times, so I'm just going to repeat it one more time. So we follow our 5-step process: inputs, outputs, set points, variables, Boolean modes, analog modes, safeties. We number our code based on how the unit's going to start, and that's what we write. However, just because we write the damper code first, or we write the temperature code second, or the fan third, does not mean that that's the order it sits in on our programming on our wire sheet. You want it located so that when someone reads your wire sheet, it's like they're reading the sequence. But you want to code it based on the order in which the system runs. Make sense? Clear as mud? Awesome. Now, as I mentioned, there's a couple strategies on how to lay out and design your code. I mentioned one of them just now. For most of you, the biggest thing you can do to impact your code and make it more readable is to lay it out from left to right, top to bottom, as I mentioned, and lay it out according to the sequence in the spec and design. If you want a sample of what that looks like, go to the YouTube video that I'll link below this. Actually, I won't link it because this will come out Monday and this won't come out till Wednesday. So this podcast will be coming out on a Monday. The episode won't come out till Wednesday. So you just have to go to YouTube, go to my channel. I'll link to my channel on the show notes at buildingautomationmonthly.com/113. You go to that, go to the YouTube page, subscribe to my YouTube channel. You get an update when it comes out on the Wednesday, or it'll already be out if you're listening to this in the future. So with that being said, let's talk about the last thing, which is the secret to fast coding. How do you get really fast at coding? I wrote the rooftop code for my programming course. I think it was about, 15 minutes, maybe 7 to 15 minutes, somewhere in there. The reason I did it was design patterns. That enables you to write code fast. When I say fast, I'm talking like Jimmy John's freaky fast. I mean, it is awesome. And the reason why is it goes based on the principle of one way to do something. Now, here's what I mean by that. When you turn on a fan, it's a Boolean on-off. There's only so many ways to turn on a fan, right? You could turn on a fan based like an exhaust fan based on temperature, or you could turn on a fan based on a condition, or you can turn on a fan based on an occupancy command. So really, when you think about it, the three ways that you will turn on fans. Now, here's the problem. A lot of programmers who are new don't know this, and they struggle writing code. One of the things that was really, really impressive for me was that the folks going through my course came back to me and said, I've learned how to program in 8 hours, and I've been doing this for 5 years. And that was really shocking to me. To be honest, I thought that folks were going to at least have to go through the course 3-4 times before really feeling comfortable with programming. But when I thought about it, it made sense. You see, in the course, I teach a philosophy of design patterns, which is that there's only so many ways to write code. And once you learn these ways, you can identify where these segments belong in a sequence, and you can do them again and again. If you want an example of a design pattern, once again, when the YouTube video is up on Wednesday, or hey, it may be up depending on when you're listening to this in the future, go check that out. I go through in great detail a design pattern, and I think you'll see why these design patterns are so powerful. Because basically, what you shift from is, rather than trying to figure out how to write the program, all you're doing is how to apply the right Lego blocks, how to apply the right design patterns. Oh, you've got a fan and it needs to start, and then you need it to have a latching alarm based on no status and having a fan command, or status and no fan command. Then you go grab the design pattern for that. You see, when you really think about it, and if you're honest with yourself as an experienced programmer, the majority of the programs you're going to write are going to be to turn on a fan or a pump or some sort of Boolean value, to command a valve open or shut, to command a damper open or shut, adjust some sort of speed control, and maybe do some lead lag or staging control. That is the majority of code you're going to write. So why not go and learn a design pattern for each type of code segment that you write, so that you can just rinse and repeat? I'm telling you, if you want to be good at programming, you need to do this. Now, how did I come up with this idea? It wasn't my pure genius. It was looking at how the IT world learns programming and then stealing how they learn and applying it to building automation. So they learn based on design patterns. When you go to school to become a programmer, or you go to a coding boot camp to become an IT programmer, you go and you learn a series of repeatable design patterns, because the philosophy is 80% of your code will be done by the majority of these design patterns, and only 20% of your code will you have to go and really adjust. But by learning and implementing these design patterns, you're going to figure out kind of how you go about doing programming, because you'll just, through osmosis, through using these design patterns again and again and again, you'll start to understand what the logic blocks are, how they're used, and how to implement the programs. So then programming becomes less of an exercise in connecting the right blocks and more of an exercise in connecting the right design patterns. Once you have this shift in your mind, and I know I'm hammering this, and I know some of you are like, why the hell is he hammering this? I'm getting tired of hearing about this. I'm telling you, it's for your own good. If you never enroll in my programming course and all you do is self-study, please start a design pattern library. Please start looking for the patterns in the code you write. It will make you an amazingly better programmer, and you will learn so much faster. I'm telling you, just trust me on this. It will make a huge difference in your career. So, design patterns, you got to use them. They're highly important, and they are the biggest difference you can make right now if you're struggling with programming. Now, throughout this episode, I have not very casually hinted at the fact that I have a programming course. And at the time I'm recording this on May 3rd, programming course has been out on the market for about a week, and I've got 140 students that have already enrolled. It's been absolutely amazing to me. I'm consistently amazed at how invested folks are at developing their skills and becoming better BAS professionals. So if you realize that programming is a skill you need to develop, and you also realize that if you go to manufacturer training, or if you spend a couple years in a trade school, you're going to come out not knowing how to program. That's the reality. And I think any of you who have been through training would agree with me on that. Then you really need to enroll in my BAS programming course. In less than a weekend, you can be writing full-fledged building automation programs from scratch. So I encourage you to check that out. It'll be in the show notes at buildingautomationmonthly.com/113. And until next time, thank you so much for being here. Thank you so much for listening to these episodes, continuing to be so engaged and giving me great feedback. I appreciate every one of you. I'm so honored and blessed to be part of helping you grow in your career. And I really appreciate every one of you who listens and tunes in every week. Next week, we're going to be starting to dive into actual optimization strategies. So that's going to be 2 series. So that'll be 2-part episodes. So episode 1, 2, we're going to be diving into optimal start stop. We're going to be diving into economizer control, reset, ASHRAE 55, 62, 90. We're going to be exploring all sorts of different staging strategies and reset strategies, basically stuff you can do to optimize your programs. We're going to be exploring that over the next 2 episodes. Thanks so much for being here. Once again, if you want to get good at programming, I really encourage you to check out my programming course. And until next week, continue to challenge yourself, continue to push yourself, continue to grow, and break through those barriers that are holding you back in your BAS career. Thanks a ton, and I can't wait to talk to you in the next episode.